If you remember how to find the determinant of a 3 by 3 matrix, that's fine. So I'll go straight to finding the determinant of a 3 by 3 matrix. And I'll use an example. Okay? I'll use an example. But one thing that you should actually understand is that when we are solving, for example, equations, I'm using this because we'll use it again where we are going very, very soon. If you are solving some equations that involve matrices, remember the matrices are of the order A, B, C, D. You know, there are these X values, X1, X2, right? It can be X and Y equals to the product matrix. Now, this is a system of equations. So if you want to solve these equations and find the value of what? The values of X, okay? What that means is that you can't go ahead and just divide, you know, this product matrix by the matrix A. No, because matrices don't divide. You get it, eh? We don't divide matrices. So instead, we invert the matrices. You find the inverse of a matrix A, B, C, and D inverse, right? Then that inverse is what you multiply by the product matrix. And that is straightforward, will give you the values of X, the X's, okay? So now let's go straight to finding the determinant, inverting the matrix actually. So we have a very interesting matrix. The matrix number is what? Is 2, 0, 5, 1. You should understand this because everything we'll do afterwards will be easier if you remember this. 2, 2, negative 2, negative 1, and 6, right? This is our matrix. So first thing is to find the determinant of this matrix. And we made mention that you could use the first row where you can pick this first number, 2, for example. You delete the row, delete the column, isn't it? You remain with the 2, 2, negative 1, and 6, right? You're following, eh?
Yes.
Plus, the next one is 0. So 0, and then we delete the row and the column in which 0 is. I'm just reminding you this. 1, 2, negative 2, and 6, correct? Sorry, and negative 1. Okay. Is it negative? No, 6, not negative 1.
Yes.
Plus 5. Okay.
So here, that is here on finding the statement on 0. Isn't it supposed to be minus 0?
No, 0 doesn't have a sign.
So it's, but if it was a number, it would have been minus, right?
Yes. You know it better.
Yeah. Okay.
You are a sharp girl. 1, 2, negative 2, negative 1. We close like this. Okay. Yeah. And we go ahead and do what? Solve the inside matrices, isn't it?
Yes. So
Find the determinant of this major diagonal minus the minor diagonal. So this will be 2 times 6, 12, right? 12 minus 2. That will be 12 plus what? Plus 2, right? You have seen it, eh? It will be negative 1 times 2, it will be negative 2. Mind you, there is a minus there. So it will be minus. It will be like this. Negative 1 times 2. Then there is a minus here. This is 12. You've seen, eh? So 12
yes.
minus. Okay. And then we have a 0 plus 5 times the 1 times -1 is -1, -1, -4, right?
Yes.
Minus the -4, which will be plus 4, right?
Mm-hmm.
You're following?
Yes.
And then from there, I'm trying to take my time so that you can understand. Yeah, if you understand this, you know, we will work with matrices almost in all the topics. You'll be shocked even when you go to calculus at some point, we'll still be using matrices. So it's the largest portion of this course, actually. This is 14 times 228, yeah? Plus, that will be -1 plus 4, 3, yeah? 3 times 5 is 15, correct? Yeah. You're following, eh?
Yes. So it's the answer is 43.
Yes, so 43 is the determinant. Okay. Now listen. I'm showing you how to find the inverse, not the determinant. The question is find the inverse. So how do you go ahead now, find the inverse? You need to come up with what you call the matrix of cofactors. A matrix of what? Of cofactors. How is it established? I want you to pay attention. Our matrix is 2, 0, 5, 1, 2, 2, -2, -1, and 6. You're paying attention, eh? Now let's go and
Very
find
nice.
the cofactor matrix. So to start with, it's in the same way. We start with the first element, delete the row, delete the column. So on this position, what are you going to have? You have 2, 2, -1, and 6 remaining, right? You're following, eh? Then when you go
Yes,
here
sir.
where there is that, we shall have what? We are going to have 1, 2, -2, 6, correct? You're following, eh? When you got the last one, delete the row, delete the column, it will give us what? 1, 2, -2, -1. Is that correct?
Yes.
And then we come to this one here. Delete the row, delete the column. What are you gonna have? You have 0, 5, -1, and 6, correct? And then we go where there is 2, eh? Delete the row, delete the column. We shall have what? 2, 5, -2, and 6, right? You're following, eh? And we go to the last one.
Hello?
It will be delete the row, delete the column. Are you following? 2, 0.
I'm able to hear, but the screen is not showing.
Oh, is it the network?
Okay.
Are you able to see it now?
Oh, yes,
You're
sir.
able to see it? Okay. So now let's go to the last row. Here where there is the 2. We delete the column and the row. You remain with what? 0, 5, 2, 2, right? Yep. Again, delete the column, delete the row. You have 2, 5, 1, 2. Again, delete the row up where there is 6. Delete the row, delete the column. You have 2, 0, 1, 2. You've seen that. Okay?
Yeah.
Are we good?
Yes, sir.
Now, from here now, we are almost there to finding what? The cofactor matrix. What you do now is just solve these determinants. Find the determinants for each of these. Okay? So this will be 2 times 6. Need 12, right? 12 minus 2 is what? 14. Is it? I'm using shortcuts now. You know how to find the determinants. 1 times 6 is 6. Minus 4, it will be 10, right?
Yes.
And this will be 1 times negative 3, 3 minus 4 plus 3. Like that, right?
Yes.
You do the same for the other one. This
So
one.
then, so this one will have 0 times 6, 6 is 0. Then minus 5, which is 5. Right?
Minus. There is always there are 2 minuses.
Yes, minus 5, which is 0, which is 5. Sorry.
Okay, 5.
Yes. Then this one is 12 minus 10, which is 2. Then this one is
hold on. You have forgotten the other minus. It's always minus.
No, I have.
Okay, so it will be what?
Oh, it's this is positive because it's 2 multiplied by 6, we get 12. Then 12 minus 10, which is 2 multiplied by 5, we get 2. Since they are all positives.
Hold on.
Right?
2 times 6 is what? 12 minus.
12.
Isn't it? Negative 2 times 5 is negative 10.
It's
You're
negative.
following?
I didn't see the negative. Oh. No, the one I have, I didn't get the negative. Okay. So it's negative 2, so it's minus 10, which is 22.
22. Okay.
Yes. Yeah. Then the other one is 2 times negative 1, it's negative 2 minus 0 is negative 2.
Okay, the next one.
Yeah. Then the last one is 10.
Negative 10.
Negative 10.
It will be 0 times 2 minus 2 times 5, which should be negative 10. It will be 0 times 2, right? Minus 2 times 5. You're following, eh? Should be 0 minus 10.
Yeah. Then the other one is math.
My copper.
The other one is it's 4. The other one so minus 10. The second one is, sorry, I went to the last one. The second one is 4 minus 5, which is negative 1. Right? Then this other one is 4.
Okay.
Yeah. Which we are done.
Okay. Yeah, so this one, This one you are seeing is almost a cofactor matrix, but it's not yet until you subject now those signs. You remember those signs? You multiply by those
The
signs.
plus.
Remember, we are not multiplying at first. We didn't multiply them when we started. You don't confuse with finding the determinant. When we started this process of finding cofactors, we didn't consider those signs, so we need to consider them. So where there is 14 is positive, positive times 14 is 14, right? Where there is 10 is what? It's negative. Negative times 10 is negative 10, correct? Where there is 3 is positive, isn't it? You remember those signs, eh?
Yes.
Where there is 5,
so
it's negative.
it's plus, minus, plus, then minus, plus, minus, again plus, minus, plus, right?
So here where there is negative 2, it will become what? Positive, right? Because there is a negative there again. It will be negative, negative. Right?
Oh.
Then this will be negative 10 because this is positive. This will be 1 positive and 4.
Minus 2, 22, minus 10, 1. I'm clear. There.
You're good?
Yes, sir.
Okay. So now from here, what you're gonna do, this is now called the cofactor matrix. You get it, eh? You're following, eh?
Yes.
Then the cofactor matrix, see, you need to form an adjoint matrix. An adjoint is basically a transpose of this. A transpose of a cofactor matrix produces an adjoint. So what is the transpose of? You know how to transpose changing the rows in 2 columns? It will be 14, negative 10, 3, right? See what I mean? Like you just change this row, first row, it becomes a column. Okay?
Yes, sir.
Then the second one will be negative for what? Negative 5,
So,
22, and 2. Then the last one will be negative 10, 1, and 4. This is said to be an adjoint matrix. Okay? Just the transpose of this, basically. Transposing the matrix.
this is an adjoint.
So when you transpose the cofactor matrix, it produces an adjoint. Okay? Then now, to find the inverse therefore shall be 1 over the determinant, which is 43, times the adjoint. That's all. You get it, eh? You know how to multiply a matrix by scalar?
Maybe it's the English.
Okay. So it is well. Multiplying a matrix by a scalar. Simply, for example, if you have a number here, 2 times a matrix here, let's say 2, 1, 3, 4, right? This simply means 2 times 2, 4, 2 times 1, 2, 2 times 3, 6, and 8. This is what we mean. You got it, right? Like this is a scalar.
The 2.
So in our case, the 1 over determinant, that's a scalar. So you have to multiply it with almost all these. But usually you can just leave it here still. It's still an answer. It's still a complete answer.
No.
A good teacher should give you all the marks. Yeah, you can't fail to multiply this, eh? 1/3 times each of these and produce.
No.
Any question?
No.
That's how you. That is how you invert a 3x3 what? Matrix. Do you have any question?
No, not yet.
Which is beautiful. Let's move on to today's conversation, the meat for today. I wanted to remind you this so that there is peace where we're going. You remember how to solve matrices using Cramer's rule, right? Where you just use the determinant over determinants. I think we had started from there. That was last premise, I think in Math 1. How to use Cramer's rule? Do you remember?
Maybe just a recap, but
A recap. As for now, let's see, or we can recap tomorrow so that we don't waste time. Okay, it's not really the main thing for this conversation, but I just wanted to get it to still remember. Eigenvalues and eigenvectors, you are still good with them. But as for today, I want to speak to diagonalization of a matrix. Okay? Since you said you went through eigenvalues and eigenvectors, right? Hello? Hello? Hello?
hello.
Hi.
Sorry, I was locked out.
Welcome back.
Thank you.
Did I hear you say that you went through eigenvalues and eigenvectors?
Yes, sir.
Okay. If you did, it's fine. Let's go straight to diagonalization of a matrix. Now, the diagonalization of a matrix simply means forming a diagonal matrix. We write on the principles of eigenvalues and eigenvectors. So diagonalization of a matrix is simply known as the spectral decomposition. Quite simple and interesting, all right? Now, they play an important role, in simplifying some mathematical operations in economics. Yeah, we will use these as we move on. You will see them better, the application of them a little bit later on. But as for now, we want to teach you how to diagonalize a matrix, okay? Get it from here that a diagonalized matrix is equal to the transformational matrix inverted. This is an inverse, okay? Not transpose, inverse. The inverse of the matrix times the matrix A, the actual matrix, multiplied by the matrix, the transformational matrix. So these are three matrices, right? You know how to multiply matrices. Matrices are multiplied row by column, isn't it? I think you remember that basic conversation. Please, if you can't remember, when after this class, just go remind yourself how we multiply row by column, those boring things. Just go do them. You'll be fine. So maybe your question should be, how do you come up with the transformational matrix T? But before we get to transformational matrix, we need to make mention that when you are solving or we are diagonalizing a matrix, simply means that you should have the eigen values in the major diagonal. You get it, eh? If it's a 3 by 3 matrix, it will be like this. Hello?
It logged me off, sir. Sorry.
You are here?
Yes, I'm here.
I was recording that. I was recording that. When you diagonalize a matrix, after solving, the result will be the eigenvalues in the major diagonal. And all these other entries will be zeros, okay? You have the eigenvalues in the major diagonal, just like that. If it's a 2 by 2 matrix, it will have these two, and these will be zeros. So that simply means, okay, the matrix has been what? Diagonalized. Okay? So I was saying how to diagonalize, how to come up with a diagonal matrix. A diagonal matrix. The formula is this one. Simple formula. It is a transformational matrix inverted, or the inverse of a transformational matrix, multiplied by matrix A times the transformational matrix. Now, maybe your challenge is not knowing what the transformational matrix is, right?
Yes.
Yeah. And that's the work of the teacher that has been hired. Question number 10.4. Let's do a quick example. We'll skip some steps because you already know them, just to help you understand. We are here, okay? Given the matrix is A, and the matrix is 4, 1, 4, 3, 1, 2, right? This is your matrix. Number 1, can you find the eigenvalues and eigenvectors that correspond to this? And also, can you come up with a corresponding diagonal matrix? That is the question. So it's a 3-in-1 question. In our twins.
Find the eigenvalues and
vectors, then and the diagonal matrix. Now, listen. The steps are, number 1, you have to find the eigenvalues. And remember how we find the eigenvalues, basically. You just deduct the lambdas in these, right? In the major diagonal, isn't it?
Yes, yes.
I'm using shortcuts. And then from there, you solve this matrix, like multiply these, cross multiply. 5 minus theta times 2 minus then minus 3 times 1, which is 3, right? And then from here, you work out this matrix, then you have a quadratic, squared minus 6 lambda plus what? 5, okay? Then you solve this matrix, this equation. This is a quadratic equation. And you know very well how to solve quadratic equations, right? You can solve them using formula method, factor method, and among others. Okay?
Yes, sir.
Okay. So when you solve them, you will notice that you will find 1 and 5 as what? As the eigen values. Okay? Is that right?
Repeat what you said, sorry.
So I've said when you solve this matrix, you will find 1 and 5 as the factors, basically, which are the eigenvalues, isn't it?
Yes.
If you're not comfortable with the shortcut, you tell them that the shortcut is too shorting.
No, the shortcut is not shorting.
And the shortcut is too shorting. Huh? Does teacher need to go through this? Ah? Are you still there?
Yes.
Okay, a quick reminder.
This is
I'll
where
use the product
I
rule.
was trying. So the product rule, we have -1 and +6, right?
Oh, the product is A times C, which is 1 times 5. So the product is 5. Then the sum is -6. Then the factors now. What are the factors?
1 and 5.
1 and 5. What one?
-1 and -5.
-1 and -5. Yes. So that's that. So when you're solving, easy. So it's x squared, or no, it's not x squared. We are use of xi. Lambda squared minus lambda minus 5 lambda plus 5. Factorize lambda minus 1, right? Minus 5 lambda minus 1, isn't it? And so you are following, eh?
Yes.
Lambda minus 5 lambda minus 1. So when you solve these, you equate them to 0. So you find that lambdas are 1 and what? The other one is 5, isn't it? This is what I was saying.
Yes.
Now, these are eigenvalues. We need the eigenvectors for each of them. Okay? Let's find eigenvectors. We'll start with the first one, where lambda is 1. If lambda is 1, in our original matrix, remember it is 4 minus lambda, 2 minus lambda, right? 1 and 3. So what are we going to do? Where there is lambda, we put 1. So it will be 3. You're following, eh? 3, 1, and 1, right?
Oh.
This will be our matrix, isn't it? Multiplying it by x1 and x2, set everything equal to 0, right?
So where
Are you
the
here?
lambda
Where there is lambda, we put the value of lambda now, which is 1. You got it, right?
Yes.
And then from here, you have these systems of equations. So you have 3x1 plus what? x2 equal to 0. You know how to multiply these row by column, right? Then the other one again will be 3x1 plus x2. So it's the same. So I said last time, you pick any of these two equations since they are similar. And we can make x2 the subject of the formula, right? So x2 will be equal to negative what? 3x1, isn't it? Hello?
Yes. I'm following.
So from here, we need to normalize, right? Normalize. There is the normalization matrix or the normalization equation that we have, which is which one? x1 squared plus
x1 squared plus
is equal to 1. We now have x2, right? Where there is x2, we'll put what? Negative 3x1.
I want to be, sorry, sir. I want to be writing the steps nicely. So then we normalize. normalize using the formula. Which is x1 squared plus x2 equals 1. Then you substitute, right?
Yeah.
I can remember.
So in this case, it will be x1 squared plus where there is x2 is what? Is negative 3 x1, right? Squared equals to 1. Okay? And we know that this square is for everything, right? So it will be x1 squared plus the negative 3 squared, it will be what? 9, right? X1 squared equals to 1. Yeah? This will be 10 what? X1 squared equal to 1. Divide through by 10, through by 10. So that x1 can be equal to what? 1 over the root of 10. Yeah?
Sir, if we moved x1, isn't it supposed to be a negative? If it crosses the sign and this other one goes inside.
Which one?
Isn't it supposed to be minus 9? Minus 1.
Minus 1. Which one is
so
coming
here
minus?
after we substituted, we squared the 3. You have x. It was x1 squared plus 9 equals 1. So
we added x1 squared plus 9x1 squared is 10x1 squared.
Oh no, it's me who made the mistake.
Don't worry, you'll be good.
No, it's me. I didn't include the x1 squared to the 9.
Okay. Okay. So we have found x1. We need the x what? X2. I think x2 can easily be found even by this same equation, right? You're following, eh? Hello? Hello?
Keeps on knocking me off. Hello? I was knocked off. I don't know.
Welcome back. So that's how we find x1, yeah?
Yes.
We need to find the x2. Okay? To find x2, we can even use the same equation above, isn't it? So you can say x2 is equal to negative 3 times 1 over root 10, isn't it? Which means the x2 is equal to what? Negative 3 over root 10. Right? You're following, eh? Have you followed?
Yes, sir.
And those are the first Eigen vectors for corresponding to eigenvalue 1. So they are 1 over root 10 and the negative 3 over root what? 10. Then let's go and repeat the process now. We put what? 5, isn't it?
So it's when we when how is it?
Kyle, when we use eigenvector 1, we found these eigenvalue. When you use eigenvalue 1, we found these eigenvectors. Now we haven't used 5. There are two values, or there are two eigenvalues, isn't it? We haven't used 5. So we need to use 5 as well. So doing 5, it will be very straightforward. It's the same step again. Remember, we still write 4 minus c lambda, 2 minus c lambda, 1, 3, right? So when you minus 5, what will be your new matrix? It will be negative.
Negative 1.
Yeah.
Negative 1,
3.
3.
Negative 3.
Negative 3.
X1, X2 equals to 0. See, John? Yeah. And so you have negative x1 plus x2, 3x1 minus 3x2, right? All these equal to 0. You're following, eh?
Yes, sir.
And these equations, if you look at them critically, they're just the same. Why are you laughing? You're laughing at critical.
The tricky part, the confusing part is the same. Like they are just so involving that they are talking about the same thing.
It's the same thing. So we can even use any of these two equations. If we use the one that is down, we have 3x1 equals to what? 3x2, right? Of course, that equals sign. We divide through by 3, both sides, so that x1 is equal to what? X2, right? You've seen now what I was saying. Even here, you could do the same. X2 is equal to x1. Now that we have done that, then we normalize. Isn't it? X1 is equal to x2. So we go x1 squared plus, where there is the x2, we put what? We put x1. You're following, eh? Okay, so that you don't get confused. X1 is equal to x2, right? So where there is x1, we put what? X2 squared. It's still the same thing, but you will see. Plus x what?
X2
2 squared.
2 squared, yes, is equal to 1. Then this is
so that x2 squared plus x2 squared is equal to 1. So that this can be 2x2 squared equals to 1. So that x2 can be equal to what? 1 over root 2, right? You have followed. We first divided through by 2, then we had to do those square root.
No, that's that, boys. I am that.
Yeah. I can't manage to teach at secondary school, eh?
You can, you're patient.
I'm very patient, eh?
Yes.
I thought I used too much of shortcuts.
No, you're very patient.
Okay, let's go ahead now. Oh, we have found the x1. Now, if we have found x2, remember we said that x2 is equal to x1, right? Which means the same value. Huh? You get the gist, eh? So which means that the second eigenvalues would what? or eigenvectors will be 1 over root 2, again 1 over root 2. Simame? Okay? Up to here, do you have any question?
No.
Now let's form the matrix. The transformational matrix you heard about, it is actually formed of eigenvectors. Okay? It's a matrix that is made up of eigenvectors. That's a transformational matrix. Right? Okay.
We are still going.
No, we remember we are diagonalizing matrices. I'm teaching you how to diagonalize. That's where we are going. Like that's the main, not what we have done. What we have done is just yeah, and those are just set steps, right? So now we have gotten the transformational matrix, correct? Isn't it?
Yes.
Have you known how we find the transformation? In short, once you find the eigenvectors, you use the eigenvectors, put them together, you find the transformational matrix. You got it?
Yes.
So now, when you hear that a diagonal matrix is equal to transformational matrix inverse times the matrix multiplied by the transformational matrix, this is what we mean. We mean, can you find the inverse of this? Okay. And you know, this is a 2 by 2 matrix, isn't it? You know how to find the inverse of a 2 by 2 matrix. Okay, that can be a big deal to you. Invert a 2 by 2 matrix. You begin by doing what? Finding the determinant, isn't it? It's the same thing. Find the determinant first. So you say 1 over the determinant multiplied by, exchange the numbers in the major diagonal, right? So it will be half over root 2 and the 1 over root 10, right? Then these, they change signs. This will be negative. Instead of negative, it will become positive 3 over root 10. Then the other one will become what? It will be negative. This one, it is positive now. 1 over root 2. Then you simplify this. You get what I mean, eh? This will be the diagonal. This will be the transpose of a transformational matrix. You get it, eh? Hello?
Yes, sir.
Now, this transpose is what you are going to multiply with the A matrix, which is this same real matrix, times the transpose matrix itself before you transpose it. Remember, there is a transpose matrix before you transpose it, eh? That is T. This same matrix here. Then you multiply it by A. Then after multiplying by A, you can now multiply by the inverse of the transpose. That is how you diagonalize the matrix. So, that's that. So you have found the transformational matrix, I've already said. So the inverse of it is here solved already. After finding the inverse multiplied by what? By matrix A, and again by the transformational matrix. In short, you are multiplying 3 matrices at once. Okay? It's like you say 3 times 2 times 5. You understand, eh? That's what you say. So your question is, how can you do this? The easiest, you can first deal with 2. Okay? You can either, first of all, work with these 2. TA, which is this matrix versus the other one, right? The transpose the transformational matrix times the A matrix. Find one matrix, right? Then the answer that you're going to find now, you multiply by the transformational matrix. Then what you will find, if you have done the right thing, it should be the answer that should give you those diagonal those eigen values in the major diagonal. That's what I was saying. You've seen, eh? So the eigen values were 1 and 5. So they ended up being in the major diagonal. And then these became zeros, like that. That simply means you have diagonalized the matrix. Okay? Very easy. Simple step. In short, as long as you remember how to find eigenvalues and eigenvector, that's a foundation. This is easy. When you just find the transformational matrix, find the inverse, and of which I had to begin by showing you how you find the inverse of the matrix. Actually, I did for 3 by 3 because it's the one that is maybe much more complex than a 2 by 2. 2 by 2 is a straightforward stuff. And you multiply by that t. Okay? So it's just a question of reminding ourselves how to deal with radicands, the radicals, right? You know how to multiply radicals. For example, root 10 times root 2. You know that this is the same as what? Root 20, right? Isn't it? Hello? Hello? Hello?
Yes, sir.
Yes.
Sorry,
So
I see the phone call.
Okay. So that's what is there, boss. Okay.
Yes.
The other way of looking at the diagonal matrix is like this. You can prove it in this way. This is another version where the real matrix A should be produced if you multiplied the transformational matrix times the diagonal matrix times the inverse of the transformational matrix. That is another way of looking at it. Eh? So if you get the transformational matrix, the diagonal matrix, we already know it from where it go. Once you have already found the eigen values, we just put the eigen values in the major diagonal, and the rest you put zeros. That is the what?
You know?
That's a diagonal matrix. You get it, right? Hello?
Yes, I'm getting you.
So if you have found the diagonal matrix, actually we always know the diagonal matrix from the way it goes. we know the expectations. We expect that in the major diagonal there should come out the specific eigenvalues. So that's what we do. Okay? And that's what we know. So this is the case. Okay? And so you can put it, multiply it with these transformational matrices and the inverse of the transformation. When you solve, you multiply these 3 matrices, they should give you matrix A again. You get it, eh? It should give you this thing again. You should prove it at your own time. Just prove it.
I'll try.
Just prove it if it will give you A. You already know A. A is 4, 1, 3, 2. Just try to prove the diagonal times the transformational matrix. Yeah, and that's that. So in short, what is the key take-home message? The take-home message is when you're working with the the diagonalization of matrices, you must, number one, be conversant or remind yourself how to work with radicals, right? The radicals, very important. Your skills of how to work with radicals